Okay, let's get going. Hope you guys had a nice weekend. I was in Seattle again all weekend. Sorry I missed some of you guys at office hours. I was in Seattle all weekend with the Navy. Luckily I didn't have to take the red eye back, which was somewhat nice, but still I'm kind of jet lagged a little bit, but not too bad. All right, so here's what we're going to talk about today. We're going to continue with graphs, and in particular we're going to do a little Unix tip of the day on symbolic links, because as I mentioned in the document for homework assignment 5, you don't want to copy the huge 250 megabyte file into your own home directory. So what you're going to want to do is do what we call a symbolic link. I had screwed it up on the document. It's fixed now, but I'm going to show you how to do it here, and you should be good to go. Then we're going to talk more about the final assignment, and now's your chance to ask any more questions you've got. You've been thinking about it for a few days now, so you can ask any more questions about it, and we'll go over some more details about possibly the speed aspect of it versus the trade-off between like speed and memory usage. The bottom line there is really that you don't need to worry as much about memory usage. More you want to worry about like how fast your searches are going to take. That's more important, I would say. And then we're finally going to go into some new things on graphs. In particular, we're going to talk about this thing called Dijkstra's algorithm, which is one of the most important algorithms for graphs in general, and something that you will see throughout the rest of your computer science career. So learn it now, because you'll see it again at some point or another. OK, questions before I begin? No? All right. So the Unix tip of the day. Symbolic links. So when you have a folder somewhere on the file system, or a file somewhere on the file system in a folder somewhere, you don't necessarily want to copy it to some other file. You might just want to use it from a particular directory. So here's what you have to do that. Okay, you can create this thing called a symbolic link, and here's the syntax. You actually do ln for link, and then -s for symbolic, and then you type the name of the file where it currently resides. That happens to be the path for where the file currently resides in the comp15 web space and file space. And then you type the name of the file that you want it to point, the one that you want to point back to it. And you can call this anything. You can actually name this anything. It will point back to the original. Okay, and that places that link in the folder that you're currently in. And by the way, this file can't exist yet. So some people are getting an error there. The file, you got to delete that. If you happen to have a file called that, you have to delete it first, or it won't create the link. But now this file will actually point back to this one, and you can treat it as if it's a regular old file. You can read it in, you can print it out, whatever. You won't be able to actually delete it. If you delete this file, it will just delete the file name, not the full file. That's by design, and you don't want to do that anyway. So that's how you do it. Let me show it to you in practice. So let's see. If I make directory homework 5, and then I change into directory homework 5. OK, notice when I do an ls, there is no files in there. But if I copy that whole thing here, and then I type that out, type that out like this. There we go. Now I've typed that whole thing out, and it's now created this little link to this file. So if I do an ls, you'll see now it exists there. Right? And not only that, if you do an ls-al, it shows you, hey, this is the file name, and then it has a little arrow and saying, really, I'm this file. So it points you to where it really is. Okay? And then you can use this as any file like you want. If you want to do more on it, more, lyrics full, etc. Right? That's that. Okay? Question, Sam? Can you edit it? You cannot edit it. So if you want to edit it, some people have said, I would leave this file as it is. But some people have said, what if I want to test, instead of on just that like 9-song Rick Astley database, I want to do it on like a song like 1,000, or a database of 1,000 songs? What you can do is you can say something like this. If you do head -n and then say, I don't know, 5,000, that will create and then the name of the file. That will actually take the first 5,000 lines and print it out. And if you pipe that to a file name like lyrics5000.txt, then it will just give you a smaller file of the first 5,000 lines. Then you have to go in and edit that file to make sure you've got the break at the end, so it doesn't screw up the actual. You got to make sure it ends on a song, and then that's it there. So if you look at lyrics 5,000, then it's all there, the first 5,000 lines of it. Margaret.
So where do you have to be able to apply the head and 5,000?
In the folder. So like I do in LS, and this is where the lyrics full database is. If I just type head and then -n and then the number of lines I want, if I just type head and lyrics full, I think it does the first like 10 lines, right? But if you say -n and then a number, that'll give you that many lines. Okay. Other questions on symbolic links or other Unix-y things? Yes, Dylan.
So it looks like the file, the link that we're saving in
Yep.
the directory we're in right now is really small in memory. Is that because is it?
This, you mean the 66 one here?
Yeah.
Yeah, because it's just a pointer that says
all it is, right?
that's the file I'm looking at. And the file system knows. If you try to type out this, it'll go, where really is it really? Oh, it's here. I'm going to print this one out. Now, if I let you have write access to it, then you could edit it. But you don't have write access to it. So. Okay. Other questions on that? OK, good. All right. So back to the homework 5 song search thing. OK. So I've actually written this program like 3 times in the last week to try to do it in different ways. I keep coming up with like new different ways of doing it. And some are really fast, and some are relatively slow. And all of them take up a fair amount of memory. Like, I think I was saying this earlier. The one that is the slowest but takes up the least amount of memory still takes about 2 gigabytes of memory, right? So it's a lot of memory. Now, the homework server happens to be a computer with 64 processors and 128 gigabytes of memory, which is good, right? Because that means that many of you can like work at the same time and not have to worry about running out of memory. Not all of you, but you will probably be OK. I mean, I think given the range of times people do things, that'll probably be all right. Question?
Well, I'm using a Mac, like a MacBook Pro.
Yes.
If I were doing this locally, how much RAM space is allocated to like a C++?
Yeah, as far as I know, you get as much as it's available. So if you have 4 gigabytes of RAM on your computer, let's say, you will get as much of that as not being used by other processes. Doesn't limit it, no. No, it doesn't limit it, yeah. I was testing it on my MacBook, and that's the way it was giving me, I have 8 gigabytes, and it was giving me up to 5 or 6 when on my worst case like tests, which was not so good. But there's a little bit of a trade-off here, right? The more time you take processing because you have, like it's about time and space. The more information you give your program to do the search, right, the more memory it's actually going to take, right? But your searches will hopefully be faster if you have a good design. And that's kind of the whole point, right? As I said, I've written this like 3 times now. And in the middle of it, I kept thinking to myself, how does Google do this, right? Have you ever gone to Google and like you notice they actually put how long it takes them to return your search? Have you ever done that? Yeah. Right? So we can try that if we want. If we go to Google and type in, I don't know, give me something to search for. Bananas. All right, B-A-N-A-N-A-A-S. Bananas. It'll spell it for me right too. That's another thing. OK, so if you'll notice, it took 1/3 of a second to search through and say, hey, there's 16.7 million results that say banana on there, right? OK, and that is like pretty darn fast, right? To search like the entire internet, right? Well, of course, it's not searching the internet. It's searching an index, which is much like what you guys are going to produce. But here's how it worked. I had to look it up because I was curious about it. When they do the search, right? They've got obviously like many thousands of servers, right? That have all these this information on it. When you push the return, actually, it's even before you push the return now. You'll notice when I start typing BAN. Right? Have you ever seen the one where you're like, what does it mean? And then, yeah, right? I mean, so, in other words, you can see what the rest of the world is looking at, and sometimes you wonder what the rest of the world is all about. But I like the one about dreaming about snakes. Right? That's a phone. I did not expect. But anyway, so what it's doing is Google's actually, while I'm typing this, right, it's actually like sending responses back to the server saying, hey, what do you think he's, what do you think he's looking for, right? So so it's doing that. But B-A-N-A-N-A-S, right? And what was that? I don't want to know what bananas, Bank of America, banana smoothie. Yeah, anyway. But when you actually hit return, right, your search goes to about 1,000 different computers, right? And what it does is each computer has a little bit of the internet index that it can get to, and it keeps all of that information in memory on whatever computer system it is. So, we talk about 2 or 4 gigabytes, right? Well, Google has, many terabytes and like numerous terabytes of like RAM that they're storing basically most of the internet in memory, right? So they have it there. So that's how they can return these searches. They send your search to 1,000 different computers. Each one has a little tiny part of its job that it's doing, and then they compile it back together and give you the result. So we should be able to do better than 0.34 seconds, right? Well, you never know. Yeah?
Theoretically, is it better to have like 1,000 computers doing a tiny job each, or a giant computer?
Oh, that's a good question. Is it better to have 1,000 computers doing a tiny job or one giant computer doing a big job? It totally depends on the problem. If you can parallelize the problem, which actually it turns out you can for this, it means if you can break it up into small chunks, then absolutely having it spread out among the most processors is possible. If we ever get around to teaching it, and I would love to teach it someday, a parallel programming course, actually if you take there's a Comp 50 course called Concurrence, which we'll talk about that. The idea that some problems you can't break up like that, right? Yeah. What does that remind me of? What was the question? Would you rather? That was it. Would you rather fight 1,000 ducks or one horse-sized duck or something like that? Is that what it is? So 100 duck. Would you rather fight 100 duck-sized horses or one horse-sized duck? I don't know. I don't know the answer to that. All right. But anyway, point is that there's an index just like the one you're going to create. There's an index just like the one you're going to create that will take up a lot of memory and will be hopefully will be fast because you've got a lot of information about it. Okay. Can we minimize the space? It totally depends on your data structure. You won't be able to minimize it too much because basically, remember, part of the trickiest, I think one of the trickiest parts about this assignment is the idea that you've got to match things with the actual lyrics themselves, and you have to print out the actual lyrics, right? You can't strip out all the punctuation and then print the lyrics out later. That's one of the issues. Yeah, Jason?
Are there ways we can, say we've created our model in which we're going to search, are there any ways, are there any tools where it's serialized and saved somewhere, or?
Why would you need to save it somewhere?
If, say we're testing our search.
Yeah.
And we want to test it like on the big 176,000
Yeah.
database, and we don't want to.
You want to test on the big database, okay.
And we don't want to do it every single time. Is there any way we can?
Is there any way you can? No, you'll have to read it in each time. But this is why you want to make sure it's working on the small databases first, then try it on the big one. Now, like I said, it takes 2 or 3 minutes probably for your database to load. But most of the time, you can figure out the problems before you get to the big database. Like the big database should only be a speed issue, not a correctness issue in that sense. Okay? All right. Yeah, Lydia.
I definitely remember you talking a lot about the speed it would take. I think it was the speed it would take to read in the database initially, and you said something about like if it's over 3 minutes, we're not going to look at it. Was
No.
that a search or the read-in?
No. So do not worry about the 3-minute limit on the read-in. Okay? It may take longer than that to read in. I think there probably will be some limit just because we can't let it go forever. But it might be 10 minutes or something like that. But it'll be something long enough that you'd have to do something pretty horribly wrong to like make it longer than that. I mean, like that's kind of the bottom line there. The searches should be very relatively quick. I was actually talking to Professor Heskett, who's had this assignment before, and he said he actually created a blacklist of words you can't search for, like I and A and all that, to minimize the idea that you have to search through every song. Like that, I can consider that too. Like we will not search for the following easy words or something like that.
Like you are going to do.
I think I'll do that, yeah. And there will still be a lot of words we could search for that, I'm not going to have a blacklist of all the easy words, but the thes and a's and i's and probably love would probably be a good one, probably in every song, But anyway, the point is that we'll probably have a little bit of that. Now, I had a lot of questions about this, both on Piazza and on emails, and then in general in the class earlier today. So I wanted to clarify what has to happen here. If you are looking for the word were, W-E-R-E, it should match, bear with me, it should match we're, W-E-apostrophe-R-E, because that apostrophe will be stripped out when you store it in the database. It should also match were with a comma or an exclamation point or anything else. I know that you didn't mean to search for we're instead of were, but that's just one of the limitations we're going to have on this database. Okay, does that make sense? We're just not worried about punctuation. The only time we're worried about punctuation is when you're printing the results. Then you have to have the results printing out with the proper lyric itself. So you need to keep all the lyrics with proper punctuation. But in your, let's say you have a hash table, hint, hint, of the words themselves, use the words that have already had the punctuation stripped out in the hash table. Question?
So if someone types in W-E-apostrophe-R-E,
Should also match this.
is it okay if they get results of the other two kinds?
Yes, it's absolutely okay if they, in fact, they should.
So that's too bad for them.
That's too bad for them.
Okay.
Yeah. I mean, if you're typing word, W apostrophe R, the good news is for most things that you would probably really want to type in, there's probably not too many of those issues,
But
right?
they have to be able to tell because they have to be able to see the punctuation.
Yeah. Another one that came up on Piazza was like hyphenated words. A hyphenated word will look like one word because a hyphen is punctuation. So it will be one word. Anything that's hyphenated will look like one word. I think I searched for A, B, C, D, E or something yesterday, and it was, or the other day, and it came out, and it was A dash B dash C dash, because that all got put down into one word. Okay? All right. So that's, let's see, that's about the duplicate words here, or not duplicate words, but words that are that have punctuation in them. You will find those duplicates in there like that. Okay. Other questions?
Like related to the hyphen issue. Like,
Uh-huh.
So say there's a song that has like werewolf with a hyphen in the middle, and someone searches where, you shouldn't return a result for that?
No. If it's got a right, you're only searching for full words, and full words are with the punctuation in them, like stripped out. So werewolf, even if it was where dash wolf, you would not get that if it was were. And by the way, I am not going to be so strict about this part of it. Like if you happen to have written it such that you've got hyphens and whatever, I'm happy to like look at your results and does it make sense, you know? But in general, it should match these things. It's just going to be easier if you tried, you know, if you tried to do it. Like what you don't want is searching for W-E-R-E and not picking up W-E-R-E comma. Like that would kind of be bad. Like that would be not so good. This is going to get looped into that as well, just because it's a punctuation. I mean, we probably could say, oh look, apostrophes don't count, and I just don't want to, deal with all the little special cases if we can help it in that case. Yeah, Jason.
Do you care whether the songs are printed out in order of like?
I only care. The only order I care about is that if, well, how should I put this? I really only care if the top 10 songs get printed out, and if there's any duplicates, that's fine. I don't care if the first one's got it probably should be the first one's the highest ranking one. I think that's probably legitimate too. You should have it sorted to that extent. Susie.
For some reason, the song places where the word is marked in sound order.
Yeah, if the lyrics database is screwed up, don't worry about that. Like if the words should be printed out in the right order according to the database. But the database has weird things in there like chorus, and it has other things that people type. Remember, this database came from like humans who like music typing it in. I mean, it wasn't some other database searcher that did. It's got human error built into it, unfortunately. Okay. Other questions on homework 5 at this point? Have you guys been meeting with either TAs or me? I know I've gotten a few emails. But you should definitely stop by the lab and talk to a TA so that you can put down who you talk to, just to go over the idea. Okay. All right. I talked with a couple people today. There's probably more. If you haven't thought of it yet, there's more to this than you are thinking. It's like a simple idea, but there's like a few levels here that you have to consider. So getting a good. That's one of the reasons we have the design document like that you have to do, which is very simple. Just lay out what you're planning on doing and who you talk to. All right, other questions on this? No? Okay. Back to graphs. All right. So when we left off on Wednesday, we had gotten to this point where we had said, okay, look, we've got graphs that are directed, we've got undirected graphs, we've got they all have vertices and they've got edges, and they can have these weights or not. Okay? If there's no weights, we can consider them to all have the same weight of 1. All right? And one of the most important graph algorithms is finding the shortest path from one vertex to another vertex. Why? Because it comes up all the time. You can have, well, we'll do a number of examples at the end where I just kind of show you real life things. But I mentioned this the other day. There's mapping applications, there's telecommunications applications, there's networking applications, et cetera, et cetera, et cetera. These ideas come up a lot, and you really want to find the fastest either distance or cost or time or whatever between two different vertices. Okay? We did the one with ones with no cost on them. Okay? But in this case, we're going to talk about another one, which is for weighted graphs. Okay? There's this guy named Dijkstra. I like his name because it's got the IJK in it. Don't see that too often. And I think his first name is Edsger or something. He's from, I think he was originally from either Denmark or somewhere, or Holland or something like that. But anyway, he one of the most famous computer scientists. He created this algorithm in the 1950s, and it was well received and actually modified and so forth. But it's still kind of like the graph algorithm that you will need to know, and you will see it again. His algorithm is known as what we call a greedy algorithm. Okay, it's trying to find the shortest path from, say, a start node to all the other nodes. And it's greedy in that what it does is at each stage, given what it knows, it says, what's the best move? All right? That doesn't necessarily always work. Right? But in this case, it happens to work. But let me show you, sometimes greedy algorithms don't actually work. But let me give you another example of a type of greedy algorithm. You guys have all made change before. Okay? You've counted out change. Counting out change is actually, if you do it such that you minimize the number of coins you give to someone, it's a greedy algorithm. In other words, you start with the highest denomination. Let's say we're not worrying about 50-cent pieces or dollars, although that still works. You start with the highest denomination, and then you go down from there, and you will actually be able to give back the least amount of coins, the fewest number of coins. Okay? I happen to believe that pennies should go away. And so should dollar bills, and we should just use dollar coins and nickels and above. But that's what they do in like Australia and Canada, I think. But anyway, if you do it this way, so for instance, if you want to make 15 cents change, 1 dime and 1 nickel, you got 2 coins. Okay, you're not going to use any pennies. You can't use a quarter like that. But what if we were to go ahead and add a 12-cent coin, which would be very silly, I think. But let's say we wanted to do that. If we add a 12-cent coin, our greedy algorithm actually breaks, right? If you want to make 15 cents change with the greedy algorithm, you go, okay, well, let's see, da-da-da-da. Oh, I'll use I don't know what you'd call it. I call it a 12 pence, or call it a 12er, or a dozer, or something. I don't know. But I don't know how to call it. But anyway, you'd end up with 1 12-cent piece, and then 3 pennies, 4 coins, when really you could do it better with just a dime and a nickel, right? So it's greedy algorithm that breaks in this case. All right, so sometimes that happens, and you will see other times when that happens. Turns out that Dijkstra's algorithm is actually greedy, but it works for certain cases, and we'll talk about which cases those are. Okay? Here's how it works. What Dijkstra's algorithm does, it says it starts at some node. Let's say we're going to start vertex 1, and it says select a vertex which has the smallest distance among all the unknown ones. And what that means is we start with none of them known. In other words, we don't know what the distance is yet. We know what the individual edge lengths are, but we don't know the distance from the first one to the particular edge yet. Okay? It picks the one with the smallest distance, and then says that the distance from that node, from the one you're at to that smallest distance one, is now known, and then it repeats itself, basically. And then it says, once it's known, it goes back and decides, well, it decides whether or not it's a good idea to use that weight. So for instance, let's look at this one. If we went 1 to 4, let's say we're trying to get to 6. We could go 1 to 4 to 6, and that would have a weight of 9. 1 plus 8 is 9. Okay? Well, look, you could also go 1 to 2 to 5 to 7 to 1, which is going to be 12, 18, 19, not a good path, right? You're still going to win out with the 9. Or you could go 1 to 4 to 7 to 6, which is 1 plus 4 is 5, plus 1 is 6. So that's actually the shortest weighted path between 1 and 6. Okay? As the algorithm goes along, it may pick a different path for 6, or a different weight for 6, but then eventually it will change it to the right one. Okay? So at the end, everybody will be okay. In the middle somewhere, maybe not, but in the end, you'll be all right. Okay? And what I'm going to do is go relatively slowly through this, especially the first example, so you can kind of get the feel for how it works. And feel free to stop me if you don't understand what's going on. Much like the table we had last week, here's how we're going to implement the table to keep track of what's going on. Okay, it's going to have the vertices down here like this. It's going to say whether or not they're known or not. And remember, at the beginning, everybody is not known, so that's false. And the distance to the start, we're going to say that the start one is vertex 1. The distance to that vertex is going to be 0 because it's the start. Everybody else has a distance of infinity, right? Infinity in this case is whatever really high number you want to make that won't be any, no distances will ever get higher than that. Generally, we make it like the highest number possible in that number system, okay, in that for that value type. Okay, so we just say that it's infinity. Everybody else is infinity. So what we do is we say, all right, here's where we're going to start. We're going to go and we're going to mark. And by the way, we're also going to mark this column here that says what was the previous one that I came from to get my current value. That's going to allow us to go and print out the actual shortest path eventually as well. Okay? All right, so here's the first step. We look at the start. Sorry that the rest aren't blue like that, but that just means I marked it true. We look at the first one, and we say, OK, I'm going to mark it known. It is now known. I do not need to change it ever again. Okay? In fact, I can't change it again. And then we say, all right, well, what are the adjacent vertices? It's going to be 2 and 4. And I can update their paths. If this one's 0, then I know that this one's got to be 2 and this one's got to be 1 because of the path. So I update that. 2 has 2 and 4 has 1. Everybody else is infinity still. Okay? So next, now that we're done with that, we go, all right, which one of the ones that are still unknown, these 2 through 7, which one has the smallest distance so far? 4 does, right? 4 has a distance of 1. And so then we take care of 4. And we go to 4 now. And we say, all right, we're going to mark 4 as complete, as known. We're going to mark 4 as known. And then we're going to say, what does 4 point to? Now, 4 points to a bunch of things in this case. 4 happens to have adjacent edges to 3 and 5 and 7 and 6. Right? And so we need to update all of those. In fact, they were all infinity before. So now we're definitely going to update them. If it took 1 to get to 4, and then it takes 2 to get to 5, the total for 5 is going to be 3, which is here. All right? Same thing for 7. It's going to be 5. 7 is 5. And for 6, it's going to be 9. Notice this is not the end result. Right? It will change eventually. All right. 6 is now 9. And then 3 is going to be 3 as well. OK? Fair enough? Everybody with me on that one? All right. Then we select V2. Why do we select 2? Well, you look at the rest of the ones, and you say, which one of the unknown ones, 2, 3, 5, 6, or 7, what's got the least distance right now? 2 does. 2 has the least distance. OK? So we go to 2. We do that one. Yeah? Somebody say wait.
So I thought you were checking from 4.
I did 4. We just did 4, right? 4, we updated everybody that 4 points to. We updated 5 and 7 and 6 and 3. Okay, they all were infinity before, so now they're all going to get new results, right? And then we update those, and then we look at which ones of the ones that are still not known, 2, 3, 5, 6, and 7, which one is the least? Well, it's 2. So now we're going to go back to do 2. We are not going to follow on and do one of the ones that 4 pointed at, or edge. Okay, this is not a table in that sense. Question? OK, yes.
What would you do in the case that 2 of them have the same length?
You can pick. If 2 of them have the same length, it's totally up to you. Whatever your algorithm happens to push out, you get that one, the next one. Yeah, good question. That'll happen here in a second. OK? All right, so we do V2. And 2 actually goes to 4 and to 5. Now, let's look at what we have to do. If we look at 2, First of all, 4 is already known, so it actually can't be less by our algorithm anyway. But even, let's see if it would have been. 2 plus 3 is 5. Nope, that's more than 1, so we're not going to change 4 anyway. Right? Let's look at 5. 5 is not known yet. It has a potential of changing. 2 plus 10 is 12, but 5 is already 3, so we're not going to change that one either. Fair enough? OK. So then, well, and then we can, now we have this choice of which we can go for, because now you look at the ones that are still not known, 3, 5, 6, and 7, and there's a tie between 5 and 3 here. Right? So we pick one. We're just going to pick 3. Okay? All right, you look at 3. Does 3 need to update anybody? Well, let's see. 3 goes to 1. Well, 1 is already known, so it's not going to change anyway. Even if it did, it would be more than 0, of course. Like it's not going to change from 0. 6, on the other hand, we're starting at 3, and then we're adding 5. That's going to be 8. It was 9. If you look on the back one, it was 9 here. Now it's going to go to 8 because it's now less. So we have to update 6. OK? We update 6. And next we're going to select 5 because of the remaining ones, 5, 6, and 7, 5 is the one with the least, the lowest cost. We pick 5. We check 5 just goes to 7. And 7 does not need to be updated because it was a better path this way. OK? Now we're going to select 7 because 5 is less than 8 here. We select 7. We mark it as known. It only points to 6. Do we have to change it again? 1, so it's 5 to here, plus 1 would be 6. 6 was 8, so it does change to 6. Right? And then there's only one left, which is 6. So we select 6. 6 doesn't happen to have anybody adjacent to it, so that it's going to. So it's we don't have to actually change anything, and then we're done. Okay? And this is the final cost. So the least cost from 1 to all these is done by the table here. Okay? Let's say we want to find the path using this table to 6. How are we going to do it? How do you trace back? 6. Previous is 7. 7's previous? 4. 4's previous? 1. And then 1 doesn't have a previous. So boom, 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 and that's your shortest path. OK, see how we can look at that? Yeah, Jason.
How much time does it take to go?
That's like the next slide. I think it might be 2 slides from now. But yeah, that's a very good question. You want to think about how can you figure it out? Big O. This is a little bit tricky, but let's put it this way. It's not quite as simple as just figuring it out. It totally depends on how we look at it. So or how we actually analyze this table. So very good question. It depends on that. By the way, here's how you print it out. Notice something about this. A, it's very short. B, it's what? It's recursive, yeah, right? Because it's easily recursive, right? Print if you're going from 6, print your previous. Print your previous, print your previous, print your previous. Oh, if I don't have a previous, stop printing. Done. Right? And actually, the printing happens at the end so that it actually prints from 1 to 4 to 7 to 6. Okay? By the way, if you look online, I did print or write up some code for this. I tried to comment it better than I've commented other code, right, in the past. But if you look at the output of when you run this program, what it does is there's a couple different things that it does. You can actually change it in the main file about what types of algorithm it runs. But it just runs a generic Dijkstra algorithm, and it prints out this whole table for you at each stage of the game. So it starts out with zeros, and then it deals with 0, marks it true, or deals with node 1, marks it true, and then goes down to the rest of them here. Okay, so you can actually see all this printed out. And then at the end, it actually prints the shortest paths as well. So this happens to be the same one I'm doing on the board. And if you look, it says from 1 to 6, it goes 1 to 4 to 7 to 6, which is what we had. Okay, so if you want to take a look at the code, feel free, and you can see how it's done. All right. By the way, in lab today, you'll also be doing some graph traversals. Correct me if I'm wrong, but it's a little bit tricky to first think about how it works. Hopefully your lab leader will explain it. But there's some parts that it basically leaves you with no code. And it's like go, and you're like, oh my gosh. But so you can figure it out. But it's a matter of understanding what's going on before you actually jump into it. Okay, but that's what the lab is on, graphing sorts of things. Okay? All right. So to get to Jason's question. Oh, yeah, question.
Is there ever like a case where you would mark a node as known that there's actually a faster path?
Is there a case where you would mark a node as known and there's a faster path? With positive weights, no. That's why this algorithm works. It does work provably so for all cases, right? You may end up with some infinities because you can't get there. Like if there were no nodes coming, let's see, there was only one thing going to it, I believe.
6.
No, well, 6 has nothing going out of it, but like I think they're here. 3 only has one pointing. If this didn't have anything pointing to it, it would still be infinity because you can't get there. You can't get there from here, right? You can't get there from the first one. But no, provably so, there's no way that this can fail on this with the parameters we have here. Okay. All right, well, back to Jason's question. If you want to know how this performs, well, it totally depends on how we actually look at the table here as we're going through. One approach, in fact, one would say it was the obvious approach, is to say, scan through all the vertices and find the ones that are still not known and check, and then get the minimum one. Okay, I mean, that makes sense. That's what you're trying to do. So that's one way to do it. Look through everybody and just take and then find which one's the minimum one. All right. Problem is, well, not necessarily the problem, but what that means is that for every phase you go through, you have to look at all of the vertices. And you're going through the number of vertices, number of phases. So it becomes a number of vertices squared algorithm in this case. Okay? So it's a v squared or n squared algorithm in this case. All right? Is that a bad thing? It depends. Last night on the plane, I was drawing this. The guy next to me is like, "What are you doing?" Right? This is my attempt at a fully like a dense graph, right? I tried to get every edge to point to every other edge, and it's harder than you think, right? What this means is the number of edges are on the order of the number of vertices squared. Not necessarily exact, but it's on the order of the number of vertices squared. For a dense graph like this, that v squared algorithm is the best you're going to do. Because really what you have to do is you still have, for all the edges, you're going to have to check out all the edges. And really, given the number of edges, you're actually doing it in like linear time as far as the number of edges are concerned. So if the graph is dense, it's not a bad way of doing it. The real deal is that most of the time we don't have dense graphs like this. Sometimes we do, some networks do, but again, that's rare that we have that. Like normally there's like, if you're talking about a computer network, for instance, normally there's like a hub and everybody talks to the hub and then goes through one or whatever. You really don't have many like directly peer-to-peer type networking things. And we'll talk about all peer-to-peer networks, but it's peer-to-peer is not necessarily a complete like dense graph like this. But anyway, best you can do for a dense graph is this method. Most graphs that are not dense, and so therefore we have to think of a slightly different way of doing this. If the graph is sparse, okay, what we have to do is we can change this such that we use a priority queue. One of the reasons we beat into you the idea of a heap and a priority queue is so that when we got to graph algorithms, we found a good use for them. Remember the idea of what we're trying to do here. We're trying to pick out the minimum of the nodes, the minimum distance. Well, isn't that exactly what priority queues do? They give you the minimum number. That's the whole point of them, or the maximum, but whatever you want. You can easily get the minimum value, which means it's great for this sort of idea. Okay? Every time we change a distance, we actually insert that vertex straight back into this heap structure that we're keeping and select the next one by doing a delete min, which we know heaps are really good at. If the minimum node happens to already be known, like let's say we changed it and then it gets known and then it becomes known and somehow it ends up back in the, well, it probably shouldn't actually end up back in there, but if it did, you would just ignore it and perform another delete min. Just ignore the one. If it's already known, then perform another delete min. Okay, it could end up in there and then become known. Yeah, it could end up being known before the next one in the priority queue gets used, which is fine. Okay, perform another deletement. I'll show you how this works. Okay, same example. Now we're going to use this priority queue to do it. We start out with a heap. We put the one we're starting at in the heap. It's a very sad-looking heap right now. Right? It's going to be even sadder in one sec, because the first thing you do, remove that from the heap. You do a delete min. Well, the only one there is that vertex, so you delete it, and that's when you mark it as known. So you delete it from the heap. You say, okay, I'm going to mark it as known, and then I'm going to take the ones I point at, and I'm going to put them into the heap. Okay, so 2 and 4 now go into the heap, and the heap goes from this to this. And remember, it doesn't matter which order you put them in, because as you insert into a heap, things bubble up and bubble down into their proper place in the heap. So the next one you take out will be the minimum. That's what's beautiful about the heap. So now you've got 2 and 4 in here. We're going to do a delete min. That's going to pull 4 off. Right? It's going to pull 4 off. 4, we said, looks at all these other ones, 3, 6, 7, and 5. And so you're going to have to deal with those. You're going to mark 4 as known and then deal with 3, 6, 7, and 5 and push them all onto the heap. There we go. So now the heap still has 2, and now it's going to have 3 and 5, which are actually they're actually the same in this case. You can do it with a heap this way if you want. And then you've got the other ones which are also in there. Okay. And then you keep going. So you're going to get the delete min, and that's going to give you 2, and then 2. The only ones let's see, are you actually changing any here? I think you're changing. No, you're not actually changing any. So you're going to do delete min for 3. Same thing. Now 3 does change 6. So notice 6 is now going to go on here again. All right, 6 is on here again, and it has a distance of 8 down here. We will eventually deal with it in some form and change it, and then we'll ignore this later when we get to it. Okay? All right, and then same thing for 5, et cetera, et cetera. Okay? Let's see, we're going to get 5, then we're going to get 7, then we're going to finally get 6, and we're going to get the first 6. We're going to at this point 6 is now its minimum, which is 6 in this case, and it had bubbled up to the top. And we're going to pull that off, not change anything, and then still have these 2 left on the heap. We're just going to pull them off. 6 is already known. We're going to pull them off, and we're going to be done. Okay? All right. Now, did we gain anything from this? I think we did. All right? I hope we gained something from this. Otherwise, why was I telling you it, right? Let's look at the running time for this one. Now, in this case, we have to look at each edge, just like normal. We always have to look at each edge. You're not going to get away from that, right? Before each edge, we're going to have to do a delete min. Well, what is the complexity of a delete min? You guys remember how you do deletes from a heap? Take the top one off, the bottom one goes to the top and then bubbles down. What is the order of that operation? Log n. Yeah, so it's log n. So for each edge, you basically do log n remove mins for the number of vertices, and you go from v squared, number of vertices squared, to the number of edges times the log of the number of vertices. So we've actually gained a fair amount there. Okay, it's better. And keep in mind, most of the time the number of edges is fairly small. So that's actually great. It goes from v squared to the number of edges being very small, e log v. This is actually not the way that Dijkstra did it first. When he actually came up with it, he came up with the v squared algorithm and published it. But give him a break, it was the 50s. It's like the second algorithm for graphs ever published, right? And so, anyway, then somebody eventually came along and said, oh, you can do it better with this priority heap and blah, blah, blah. And so there you go. Okay, questions on that? No? Yeah?
If it's like a really dense graph, does this end up being worse?
If this is a really dense graph, does it end up being worse? I don't know if worse is the right idea. It probably devolves basically into the same one, because really what that means is that well, let's see. Does it end up worse? It may end up worse because the graph gets, well, I'm not actually sure. I don't want to answer that without being sure on it.
Yeah, I think you just
Yeah.
need to know how many edges are in the graph.
Yeah, I mean, it would be v squared, edges in the complete graphs. Then it would be v squared log v. So it's actually worse in that case, yeah. Yeah, so that would be worse in that case. Yeah. So if you have a really dense graph, don't use this method, I guess. That's the idea. Plus, there's overhead of using a heap. It's easier to not use a heap. Jason, you had a comment?
Oh no, I was trying to do that.
Okay. All right, good. Okay, so that's Dijkstra's algorithm in general. Okay. We talked a little bit about negative edges the other day. Turns out that Dijkstra's algorithm actually doesn't do so well if you have a negative edge in there. All right, let's take a look at this example. Keep in mind, if you were to do this example like this, you would start at 1 again, because that's the starting one. Start at 1, mark that as known, and then go to 4 and 2 and say that that one's 1, 4 is 1, and 2 is 2. So far, so good. That's exactly what we did before. Now we go to the one that's the least one of all the knowns, or sorry, the least of all the unknowns, right? And the least of all the unknowns is which one? It's still going to be 4, because what did we say at the beginning all of the distances were for these? Infinity, right? So this one, even though you say, oh, look, it's got a negative 40 in there, let's deal with that one. No, you can't, because 7 is still infinity as far as the algorithm is concerned. So you say, OK, now you deal with 4, and you mark 4 as known. Then eventually you get over here, and you go da-da-da, and then you go to 7, and it's got a negative 40 in there, and it should bump 4 down from 1 to like negative 39 or negative something, right? So it should bump it down, but it doesn't. It actually doesn't work right for this one. Darn. Is there an easy solution? Can we think of an easy solution for this one? There's a somewhat obvious solution that might work. Yeah.
So you just, instead of marking it as known, you just keep the shortest, you keep whether or not you visited it before?
You keep whether or not you visited before. That actually would work.
And then keep going around until you get either the same thing.
Keep going around until you get the same thing. Yeah, so that is actually a very good way of doing it. So that actually changes the algorithm. Without changing the algorithm, is there an easy way to solve it? What do you think back there?
Can you change the value of the keys?
Why not?
So I would increase the value of every key by the absolute value of the
Yeah.
negative key.
OK, so it wouldn't be any more negatives, right? Let's actually go one step. Let's make it. It doesn't matter. You could do it. I did it. When I thought of it, I did it by adding 41 to everybody. So at least you'd have positive ones. But you could certainly add 40 to everybody. And then would that work? Now everybody's positive, right? Well, that's a great answer. It happens to be the naive answer, as the book says. But that's not to say that it's a bad answer. I probably shouldn't have put that in there like that. But no, that's a great answer. Here's the issue, though. Notice what happens, right? So we go from, let's add 40 or 41. Let's add 40 to each one. This becomes 42. This becomes 50, right? Now, instead of just going up by 40, we've gone up by 80 to get to here, right? So every time you go an extra length, you're actually adding twice what you really should be adding. So it's not quite that. It's not like that actually doesn't work. So notice here, so still we had hoped that this path would be less than this path. That was the idea, right? To go back here, this path was 1, but really we could do it in a negative. Negative 40, 30, negative, what is that? Negative 32 or something like that, right? Or no, 12, negative 40, what is that? Negative 28 or whatever, right? So you should be able to go this way versus this way. But if you do it this way, you still end up running into that problem because you've kind of doubled up, right? 43, 51, 47, and 1 is still more than just going 42. So great idea. Unfortunately, it doesn't work. But that's the right way of first thinking about it. OK, so you can't do it that way. So it does look like we're going to have to go with Sam's suggestion to change the algorithm itself. OK, and you can do that. OK, there isn't a particularly easy one, unfortunately. But what we can do is we can say, let's kind of take this combination of weighted and unweighted algorithms. In other words, as Sam said, forget about the fact that we have anything known. You just can't know anything until you've gone through everybody. Okay? And by the way, we can come up with a new algorithm that's going to cream us as far as the running time, as it turns out. But we can do it. And sometimes getting the job done is important. Okay, even if it is a bad cost. All right, so what are we going to do instead? Forget about those known ones. Just say you're not dealing with those anymore. Because we may have to change our mind later. In other words, the greedy algorithm no longer working. Okay, greedy algorithm is not working properly. Okay, whoops, here's the idea. We use a queue. Okay, use a queue. And at each stage here, what we're going to do is dequeue the vertex. So we place S on the queue. This, by the way, is very, very similar to what you will do in lab today. So pay attention here, because this is kind of the, you won't have to do all this like checking, but the idea is similar. It really is a breadth-first search that we've done before. Place the first one on the queue, first vertex on a queue. At each stage, dequeue a vertex, and then find all the vertexes that we need to adjust their cost for, even the ones that we've possibly seen before, adjust their cost, and then put them back on the queue. That's where you kind of lose in terms of the time complexity, because you got to throw it back on the queue. Okay, you put it back on the queue, and then update the, you put it back on the queue, and by the way, you set a Boolean just to say, hey, I'm already on the queue, don't worry about putting me back on there. And then you repeat the whole process until the queue is empty. So what it means is, for 4, for instance, we may have to put 4 back in the queue a couple times to make it end up being the right one. Okay, you'll see how it works here in a second. Same example again. All right, same example. Here's our queue. What are we going to do? We're going to put the first one in, and then we're going to dequeue it immediately. Okay, we dequeue it, and we look at which ones it points to. 2 and 4. Same idea as before, right? And now you've got 2 and 4, and you can update 2 and update 4, etc. Okay, that should say infinity still. All right, and then we're going to bring 2 off. Nothing actually changes in this case, because 2 actually, and this guy changed some of the arrows here to make it no cycles. Notice you can't get, once you deal with 40, you're not going to end up going back anywhere that can get back to here. So there's no cycles, negative cost cycles. OK, so we're going to dequeue 4 and then check the weight for 6, because 4 only points to 6. And change if we need to. We don't need to. So then we check 5. Oh, no, we do need to, actually. Sorry. We change 6. So 6 goes on the queue. Then we take 5 off. And then we end up taking 6 off. Then we end up taking 7 off. When we get 7 off, notice what happens. So here's 7, and we go, holy smokes. Now we've got huge negative value here. We've got to change 4. We've already dealt with 4. Too bad. We change it. We put it back on the queue. OK, so 4 gets put back on the queue. And now we've got 4 on there. We take 4 off, and we go, well, what could have changed? Because we just changed it. We have to then reevaluate it. What could have changed? Well, hey, guess what? 6 changes too. So we're going to look at 6 and put 6 back on the queue. This is where the time complexity gets a little bit bigger. 6 goes back on the queue. Now we look at 6, and luckily for us, it doesn't point anywhere. So we're good to go. Okay? And then we're done. Now, was it true that this path is now the least path? 1 to 2 to 5 to 7 to 4. I forgot to update this column. Sorry. 1 to 2 to 5 to 7 to 4. Well, let's see. That has a cost of like negative something. It turns out negative 22. And there you go. Right? Is it negative 22? Oh, I forgot about the 6. Yeah. Negative 22 in there. OK? And that's not 1 like it was before. So this actually works now. Comes at a cost. OK? And the cost is not pretty to deal with, but we can do it. Yeah?
What if we had a cycle?
Ah, good question. In fact, I believe that's the next one. Negative cost cycles, you're in trouble, right? If you had a negative cost cycle, you would keep going forever and keep queuing and queuing. What you have to do is make a call. You have to say, all right, I got to stop at some point. And so you make a call, and like one of the ways you can do that is you can say, if every vertex has been seen the number of vertices plus 1 times, you know that you've at least dealt with at least one of those times, so we're done. Then you stop it. Yeah, good question. Did you have a question too?
So, when you were calculating, when you went to update values, what did you do to update the values?
Yeah, this is kind of fundamental to this whole thing, right? OK, so let's look at, we are now at, let's go back here and do V4 again. OK, so we're at 4. OK, 4 has a value of negative 22. You dequeue 4. And you say, what does it point to? OK, it points to 6. Well, what is the value of 6 right now? 6 is 9, right? It takes 8 to get there. But if I'm at 4 and I get negative 22, I can add negative 22 to 8, right? and I will get the value that's less than 9. In fact, it's negative in this case. Okay? And that's how you do it. So you look at them all, and you update them based on how much they're going to cost me to get from where I am to there. Is it less than what it already says it is? Then you update it. The whole point is, it's not 8 to get to 6. It's actually negative 14 to get to 6. You add your value to the value that it takes to get there. And if you want to look at the code itself, it's all written out in the code step by step. So it shows you how it's done in the code. Good. All right, other questions on this? This is Dijkstra's algorithm kind of in a nutshell. Okay. What's the running time here? Well, actually, did I miss one here? No. The running time here, you could DQ as many as the number of vertices per edge, right? So each edge, you may have to look through all the vertices and DQ them because you put them, everybody changes for each edge. Therefore, you have to put them all back on the queue, which means the running time now is on order of the number of edges times the number of vertices. And so it's not so good. Much worse than order E log V. It's now E times V, which is not so good. But most of the time, graphs do not have negative vertices. So you're OK most of the time. All right? Good. No negative cost cycles. All right. So that's Dijkstra's algorithm. Again, you will see this in other classes. If you take a networking class here, you will absolutely see this, Dijkstra's algorithm again. If you take algorithms, you'll probably hammer it again. And then some of the other classes. So you'll definitely see this algorithm again. And in real life, we see it all the time. Here's some examples. Right? Shipping. Let's say you have to get a package from here to Djibouti. Right? In fact, it's actually what's nice about that is because there's a US base there, like you can send US mail to the base in Djibouti. So like relatives of mine when I was over there and friends of mine would send me like packages, and it was just regular mail as if it was mailed to Massachusetts or something. So that was kind of nice, but only because it was a military base. But anyway, let's say you want to ship something from here to Africa somewhere. Well, there's lots of different ways to do it, right? You can go by plane, you can go by boat, you can go by truck for part of it, and then by boat, and then for truck some more, and for a plane. Well, all of those have associated costs with them. It might be time, it might be money, it might be whatever. You'll do a graph of this to try to minimize those costs. Okay? And trust me when I say that UPS has experts in graphs, because they have to know how to do this thing. Did you guys know that UPS trucks generally don't turn left? You know that? Why? Yeah.
Where the driver's seat is, I guess?
No, not because where the driver's seat is. Although that might have something to do with it, but yeah.
Because when you turn left, you often have to wait for the cars to come.
Yeah, you have to go across traffic. Yeah, if you figure out your graphing algorithm such that left turns have a huge cost, well, go right most of the time. So their paths are generally right turns. Yep.
They train the drivers to do that, or they just think that?
they train their drivers to do it. No, they take out the blinker. When you do a left blinker, it's really loud and obnoxious, so they never want to do it. It's all computerized now, so the driver knows what his route is all day, right? So, it's circular, like, yeah. Maybe they shock him every time he turns a left. Trains him. Okay. Anyway, so that's an example of who might use these things. Computer networks, of course, they're going to use these routing algorithms. When you want to get a packet from here to California, a computer in California, right? It's got to go through 100 other computers, maybe. Well, the routing path that takes is really important. In fact, it's also important when a computer breaks or goes down. Like you have to route around it, and you have to know that I want to go this way instead of this way because it's a shorter path, et cetera. Okay? And of course, telephone networking, we already talked about that. Do you need to go to the satellite? Is it about cost? Maybe you're on some carrier that costs more, et cetera, right? And telephones basically are computer networks now anyway, so that's that. If there is some sort of cost differential and you have various paths, you're probably going to use something like Dijkstra or another similar type algorithm. Obviously, you've got other, like mapping, huge, right? Just mapping in general. You want to look at a subway system, right? So government center happens to be closed right now. Like how do you get from here to the airport? Right? It's not quite as easy as it used to be. Well, it's never been quite easy from here, but the point is you have to figure out some other route, and you'd need to do some sort of shortest path distance. If you want to look at a maze, if you want to figure out a maze that has multiple solutions, maybe you want to figure out the shortest path in that maze. That's the shortest path algorithm. I don't know that Dijkstra necessarily works perfectly well on that, but other shortest path algorithms do. And this isn't the only one. It happens to be the the one we all study and one of the better ones, but there are other ones as well. I read something that said that you guys know UAVs, like the unmanned aerial vehicles. When they're all up in the air, they need to kind of know how to avoid each other, right? Well, they use graphing algorithms to try to find the shortest path without bumping into another UAV. It's a good idea. Did I tell you when I was in Djibouti they had UAVs like 60 feet from me with like bombs on them? It wasn't too fun. I mean, I didn't really care that much, but it was still a little scary. Something that flying around without a pilot that has a bomb attached to it. Not too fun. Okay, anyway, so that's the examples. Now, graphing algorithms are not completely solved. I mean, people are still using these algorithms. This was a paper from 2000, which is not that recent, but recent enough that it wasn't like the 50s, right? They're talking about like using this on public railroads. In fact, I think this paper was about using Dijkstra's algorithm for when people go onto a website and try to figure out which train they want to take, and it has to handle all the different solutions. And like, let's say somebody buys a ticket, then it needs to update the thing, and then maybe the train's full, and blah, blah, blah. So this goes into all those details. So people are still working on these things. Okay, still working on these ideas. Right? And I guess that's it, references, right? If you didn't understand or want some more details about I want to see more examples of the Dijkstra's algorithm in action, that, where is it here? The visualization website that we've seen a bunch of times in here does a pretty good job. It does it for weighted, unweighted, directed, undirected, all that kind of stuff. So that's good. All right, other questions? Graphs, homework 5, anything else? Labs? No? All right, I'm letting you out a little early today on this nice day, finally.
Any word on in-person?
Oh, I know. I talked to Bruce today about in-person grading. Still working on it. We're trying to figure it out. We'll get to it very soon. Thanks for the reminder, though.